Ever find yourself looking at a really complex tech and just feeling lost, like trying to understand a race car engine?
Yeah, it happens. A lot of data centers can definitely feel that way.
Right. Super powerful, super complex. And while some of this stuff might seem, really niche, there are actually universal ideas in there. Things about efficiency, security, smart design that apply almost anywhere.
Absolutely.
So today we're going to do a deep dive. We're looking at core concepts behind VMware Cloud Foundation VCF. It's a huge platform, powers a lot of the cloud stuff we use every day.
It really does.
And we're using kind of an interesting source, some really precise technical details, actually drawn from practice questions for a specific VMware exam. But these details, they give us a fantastic shortcut to understanding how these big systems are built.
And that's spot on. Because whether you're deep in IT architecture or, frankly, just someone using digital services, which is, let's face it, everyone,
Pretty much all of us, yeah.
understanding these building blocks is surprisingly important. These aren't just abstract ideas. They underpin, streaming movies, online banking, everything.
Mhm.
And the specifics we'll get into today, they actually reveal these bigger principles about how systems are designed, how they're optimized. So our mission today is basically to unpack these concepts, connect the dots for you, and show why these technical insights actually matter.
Okay, let's jump in then. VMware Cloud Foundation, VCF. It's powerful, sure, but what really makes it work? What are the core building blocks? We should probably start with this idea of a workload domain.
Right. The workload domain, think of it as a logical container. It's self-contained, basically.
Okay, a container for what?
For your compute, your storage, your network resources, all bundled together logically. And here's the really critical part. Each workload domain gets its own dedicated vCenter server instance.
Its own vCenter. Why is it so important?
Management isolation. That's the key. It means what happens in one domain, say, for one department or application type, doesn't accidentally mess up another one.
Gotcha. So like fault-tolerant security keeps things separate.
Exactly. Essential for that, and also for letting different groups manage their own resources within the same bigger infrastructure. And just to clarify, it's not usually just one server per domain. For most virtual infrastructure domains, you're typically looking at a minimum of, say, 4 hosts.
4 hosts, okay.
Yeah, for redundancy and performance. And another thing, while you might use tools like area operations for networks to see what's happening network-wise, the domain itself isn't directly managed by that tool.
Okay, so you've got these isolated domains, each with its own vCenter managing things inside it. But what pulls it all together? What's the master controller for the whole VCF environment?
Ah, good question. That would be SDDC Manager. That's really the core management tool for the entire Cloud Foundation stack.
SDDC Manager. And what's its main job?
Its primary role is automated lifecycle management. Think deploying, patching, upgrading, all the key pieces like vSphere, vSAN, NSX.
Across the whole SDDC.
Across the whole thing, yeah. It ensures everything stays consistent, compliant, and up to date together. vCenter manages its vSphere bits, NSX Manager handles the networking parts, but SDDC Manager is the one that orchestrates the lifecycle for the entire software-defined data center end to end.
Right, so it's the conductor making sure the whole orchestra plays in time.
That's a great analogy, actually. It provides that overarching automation that the individual component managers don't.
That really gives you a sense of how these huge environments stay manageable. It's less about clicking buttons everywhere and more about, automated orchestration for efficiency and keeping things stable.
Exactly.
Okay, we've touched on compute and the overall management, but what about storage? That's obviously critical. Let's dig into vSAN a bit. How do admins keep that storage layer running smoothly?
Right, vSAN. For keeping tabs on its performance and health, the dedicated tool you'd use is the vSAN performance service.
Performance service, and what does that tell you?
It gives you really detailed metrics, things like latency, how long operations take throughput, how much data moves, and IOPS, the number of operations per second.
Okay, the key performance indicators.
Exactly. And it gives you these numbers at different levels, the whole cluster, specific hosts, even down to individual disk groups or VMs. That granularity is super important for finding bottlenecks quickly.
So you can pinpoint where the slowdown is. Monitoring's one thing, though. What about actually improving vSAN performance? What works? And maybe, what are common mistakes people make?
Good point. There are really 3 key actions that make a difference. First, you've got to verify and adjust your vSAN storage policies. These policies need to actually match what your applications need, right?
Policies matching the workload. Makes sense.
Second, you obviously need to use that vSAN performance service to monitor things and spot those bottlenecks we talked about. You can't fix what you can't see.
Monitor constantly. Yeah.
And third, if you genuinely need more horsepower or space, you add more hosts or capacity disks to the cluster. Simple scaling.
Okay, so check policies, monitor, add resources if needed. What doesn't work so well?
Well, sometimes people try things like consolidating disk groups without really thinking it through, which can backfire, or just, making sure there's a mix of flash and spinning disks in a group that alone doesn't guarantee better performance. The overall design matters more. It's about smart adjustments, not just shuffling hardware.
That brings up something pretty fundamental about storage, how space is actually allocated. The whole thin versus thick provisioning thing. Can you break that down? Why does it matter in these big environments?
Sure. The big advantage of thin provisioning is efficiency. It allocates storage space on demand.
On demand. So like only when you actually write data.
Exactly. Think of it like you reserve the possibility of using, say, 100 gigabytes, but the physical disk space is only consumed as you actually fill it up.
Okay. Pay as you go.
Pretty much. This means you use your overall storage much more efficiently, less waste. Thick provisioning, on the other hand, grabs that full 100 gigabytes of physical space right away, even if it's empty.
Reserves it all up front.
Right. Now, thick might offer slightly more predictable performance in some edge cases, but the main benefit of thin is saving space, and therefore often cost. It's crucial, though, thin provisioning doesn't automatically mean better performance or more IOPS. It's about space efficiency.
Got it. So it's really about maximizing the use of that expensive storage hardware, which obviously impacts the budget in a big way.
All right, let's shift perspective a bit. We've done storage. What about managing the compute resources dynamically, keeping things balanced across the whole infrastructure?
Yeah, that's where vSphere DRS comes into play, Distributed Resource Scheduler.
DRS, and its main job is?
Its primary goal is to balance compute workloads automatically across the hosts in a cluster. It's constantly looking for the best placement for your virtual machines to optimize performance.
How does it do that balancing act?
It uses vMotion, that live migration tech, to automatically move VMs between hosts without downtime. So if one host gets too busy, DRS can just shuffle some VMs over to a less loaded one. So it keeps things running smoothly without admins having to constantly move things manually.
Exactly. It reduces manual effort and ensures resources are used efficiently. But it's important to know what it doesn't do. DRS isn't for high availability. It won't restart failed VMs. That's a different feature called HA.
Okay, not HA.
And it's not about encryption either. Its focus is purely on that dynamic load balancing for performance.
Makes sense. So DRS handles the balancing. But what about keeping all those hosts configured the same way? If you have dozens or hundreds, how do you avoid them drifting apart in settings? That sounds like a nightmare.
It definitely can be. That's precisely the problem that host profiles in vSphere solve.
Host profiles, like a template.
Exactly like a template or maybe a blueprint. You define the desired configuration networking, storage settings, security parameters, all that stuff in a profile. Then you apply that profile to your hosts.
And it makes them all conform.
Yes. It ensures all the ESXi hosts in your cluster have consistent settings. This massively reduces configuration drift, which is that problem where hosts slowly become different over time, leading to weird issues and making troubleshooting really hard.
So it locks down the configuration for consistency.
Right. Host profiles aren't used for moving VMs around or managing vSAN directly. They are purely about ensuring that baseline configuration consistency across your hosts.
That really highlights how automation helps reduce human error, doesn't it? Ensures things are stable, predictable, crucial when you're running important stuff.
Absolutely essential for predictable operations at scale.
Okay, let's move into something always critical, security, and what happens when things go wrong, diagnostics. Let's talk VM encryption first. What do you absolutely need to have in place to encrypt a virtual machine in vSphere?
Right, VM encryption. There are two prerequisites that are absolutely non-negotiable. You can't do it without them.
Okay, what are they?
First, you need a key management server, a KMS. And crucially, vCenter server has to be configured to trust that KMS.
The KMS, that's where the encryption keys live.
Exactly. It generates, stores, manages the keys. No KMS, no keys, no encryption. It's the foundation.
Makes sense. And the second prerequisite?
The virtual machine has to be powered off. You can't just flip an encryption switch on a running VM. You need to shut it down first to apply that encryption policy.
Power it off first. Okay, so things like how much RAM it has or the specific ESXi version, those don't matter for enabling encryption itself.
Nope, those aren't the core requirements. It really boils down to having that trusted KMS and the VM being in a powered-off state.
Got it. Control the keys, apply the change when it's static. Now, what about data in motion? We talked about vMotion moving VMs between hosts. How do you secure that process?
Ah, yes. Good question. That's where encrypted vSphere vMotion comes in. Its specific job is to prevent man-in-the-middle attacks while a VM is migrating live.
So someone snooping on the network during the move?
Precisely. Encrypted vMotion encrypts the entire data stream as the VM's memory and state are transferred across the network between hosts.
Okay, so it secures the transfer itself. Does it make the migration faster or anything?
No, not really. Its purpose isn't speed. And it also doesn't encrypt the data inside the VM's disk. That's what the VM encryption we just discussed handles. Encrypted vMotion is strictly about protecting the data during that live migration event.
Clear distinction. Okay, let's shift to troubleshooting. Imagine a practical scenario. You've got a network connectivity issue in your VCF environment. Things just aren't talking. You're using a tool like area operations for logs. Where do you start looking? Which logs are most likely to hold the clues?
Okay, network connectivity problems. Yeah, that's a common one. When you're digging through logs for that, you'll typically focus on three main types.
Three main types. Which ones?
First, check the ESXi host logs. These are vital for anything related to the physical network cards, the drivers, or basic host networking configuration. Could be a simple link down issue there.
Host logs first.
Okay. Second, you'll want to look at the vCenter server logs. These can show you management plane issues, events related to the VMs themselves, or problems with how vCenter is configuring or seeing the virtual network.
vCenter logs next. Got it.
And third, especially in VCF, you absolutely need the NSX manager logs. Since NSX handles the software-defined networking and security firewall rules, routing overlay networks, its logs are crucial for diagnosing anything beyond basic connectivity.
NSX logs for the software-defined part. Makes sense. What about things like vSAN logs or SDDC manager logs?
Well, they're definitely important for overall system health, don't get me wrong. But for a specific network connectivity problem, they usually aren't the first place you'd look. Your prime suspects are the ESXi, vCenter, and NSX logs.
That really drives home how layered these systems are and how knowing where to look is key when, things inevitably go sideways. It's about precision in troubleshooting.
Exactly. Maintaining these robust systems requires that deep understanding of security layers and targeted diagnostic methods.
So here's something to think about. How might really understanding these kinds of back-end technologies, the plumbing, the engine room, actually empower you to innovate or solve problems in ways you hadn't considered before, just because you now have a better sense of what's possible under the surface?